Hello and welcome to the third video in vector algebra, chapter 1 in electromagnetics. This video will be about vector multiplication. So when we talk about vector multiplication, we keep two things in mind: dot product, or often called scalar product, and cross product, often called vector product. So let's start with dot product. Let's say we have vector, let's call this vector A, and a second vector, vector B. And there's an angle between these two vectors that is when we connect the vector from tail to tail, an angle form. We take the smaller angle, not the bigger angle. Now, dot product says, if we take the magnitude of these two vectors, so the magnitude of vector A and the magnitude of vector B, and multiply them together, and we took the cosine of the angle AB, we get what is called the dot product, often expressed as A dot B. And that is the dot product. Notice how here at the end we don't have a unit vector, even though these two are vectors and they contain unit vectors. But when we multiply them together in a dot product, we do not get any unit vector in here. And that is because dot product gives us a scalar output. Scalar output. Even though it is two vectors multiplied together, we get a scalar output, not a vector output. Now there's another way to find the value of the dot product, an easier way. Let's say we have vector A with the magnitudes, with the components of AX, AY, AZ, and vector B with the components BX, BZ. And we want to find the value of A dot B. It is as easy as multiplying like components. So we multiply AX, BX plus AY, BY plus AZ, BZ, and we get the value of A dot B. Now these will yield normal numbers, scalar numbers, not vectors. As you can see, there are no unit vectors. So the answer will be added up together to a single scalar number, no unit vectors. It will be like digits, just magnitude, no direction. Now, we've mentioned before that the value of the dot product depends on the angle between these two vectors. So let's say we have theta is equal to 0. In other words, vector A, and let's say vector B is in whatever this color is, on top of each other. Hence, they are parallel to one another. They're both in the same direction. The cosine of that value, theta, will be 1, the maximum the value a cosine can have. So when they are parallel, we get the maximum value. However, when theta is 90 degrees, when these two are perpendicular to one another, the cosine of the 90 degrees angle gives us 0, the minimum value of the dot product. And anything multiplied by 0, if you plug in 0 here, you get 0. So when the two vectors are perpendicular to one another, the answer is 0. You get nothing out of it. You don't get nothing, you get the value 0. And when they are perpendicular to parallel to each other, you get the maximum value out of the dot product. Now, the dot product properties. Luckily, the dot product is commutative. So the order of multiplication doesn't really matter. If you multiplied A dot B or B dot A, it will give us the same answer, even if we switch the order between the two vectors. It is also distributive. If we have A dot B plus C, we can distribute the dot product between these two values. So if we distribute the dot product, we get A dot B plus A dot C. And don't forget, these are all vectors. They are not scalars. Other property of the dot product is if you multiplied the vector by itself, so A dot A, you get the magnitude squared as an answer. In the third property, which is about unit vectors. Now, remember, as I said above, about multiplying perpendicular vectors to each other. And as you may know, the unit vectors are perpendicular to one another. So AX dot AY share 90 degrees angle, and AY dot AZ share 90 degrees angle, and AZ dot AX share a 90 degrees angle. Hence, when you dot product any of the three unit vectors together, you get a value of 0. And if you multiply any unit vector by itself, or any unit vector with a similar unit vector in the same direction, as we said in the property before that, when you multiply any vector by itself, you get the magnitude squared. And the unit vector, essentially, it's a smaller vector with a magnitude of 1. And 1 squared is still 1. So when you multiply any unit vector by itself, AX dot AX or AY dot AY or AZ dot AZ, you will get 1 as an answer. And the unit vectors will quote unquote disappear. Not really, but they're no longer in the equation. And when the unit vectors are gone, we don't have a direction anymore. We only have magnitude. So the answer will be a scalar unit. And that's why the dot product gives us a scalar output or a scalar product. I'm going to skip the definition of cross product right now, because I don't think you will understand what it is from the definition. But I'm gonna try to explain it in my own way. Hopefully, it will be the good way. Cross product is expressed as A cross B. And this will equal to the magnitude of A multiplied by the magnitude of B. So far, it is just like the dot product. However, here we have sine theta instead of cosine theta. And theta is the same theta above. It's the smaller angle when we put the two vectors from tail to tail. We also have an extra component in the cross product, which is a vector unit component, and it's called A n. Okay, let's say we have two vectors, and there's an angle theta between them. This is vector A, and this is vector B. The cross product says, if you bring the magnitude of vector A and the magnitude of vector B, multiply them together, and multiply the sine of this angle, and you multiplied unit vector an, it will give the answer. Now, you know how to get the magnitude of these two vectors. Now, let's talk about sine theta. Let's discuss when theta is equal, let's discuss when theta is equal to 0. What happened? Sine 0 angle will give us 0. And when theta is equal to 90, it will give us sine 90. And sine of 90 degrees is 1. Big difference. Thus, when the vectors are parallel on top of each other, the value that we will get is the minimum value, unlike the dot product. And the answer of the cross product will be 0. And when they are parallel, that's right, parallel, when they are perpendicular to one another and have 90 degrees angle, we will get the maximum value, whatever it may be, from the cross product. So I'm going to write here max. Now, what about an? Well, an is the normal unit vector. Now, what is normal? Well, the normal in vector algebra means the perpendicular. Now, what is the perpendicular? Like, they are perpendicular to one another. Well, let's say they are. Well, the vector product says, if you multiplied two vectors together, the answer will be an additional vector that will be perpendicular to both of these original vectors. Let's explain that. Let's say you have a vector on the x-axis, on the y-axis. Let's call this vector A. And you have another vector on plane on the x-axis. The x-axis, y-axis. And you want to cross multiply them together. So A cross B. This will give you an additional vector. Let's say it's called C. And it will be in the z-axis because it is perpendicular to both of them. It is perpendicular to vector A and perpendicular to vector B. And what is perpendicular to vector A and vector B? In this case, it is the z-axis. However, it could be positive z or negative z. And we will talk about that in a second. First of all, we need to discuss how do we cross multiply. There is this definition of it, but there's another additional way, which is the main way to cross multiply anything, any two vectors. So A cross B, vector A cross vector B, equal to, first of all, we need to define the vectors. Let's say vector A is in the xy plane, xyz plane, or the rectangular plane, or the Cartesian plane. They are all the same plane, just different names for the same plane. So it has ax, ay component, and az component. It also has, B also has bx component, by component, and bz component. Now, since they're both in the same coordinates, which they have to be, we write the unit vectors on top. Say ax, ay, and az. And then we write the components of the first vector that is multiplied. In this case, it's the vector A. So we write ax, ay, and az. Then we write the components of the second vector. So we say bx, by, and bz, and then we close it. Mind you, this is not a matrix. And how do we solve this? First of all, you open a parentheses 2 and you close it. And we're going to start with the unit vector ax. Now, this new vector, let's call it vector c. C is going to have a component in the x direction. So it's going to have a unit vector ax. You go here and you find ax. It's on the corner. And you cross it horizontally, and then you cross it vertically. What we're left with is these four components. What do? We go from left, we go to the right of the vertical line. What comes after the cross is ay. So we say ay and multiply it with the diagonal component. In this case, it is bz. So we write multiplied by bz minus az cross by. We go from a z multiplied by by. So az by. And we're done for the ax. Plus, you open a second parentheses and you write a y, because that's the second unit vector. You find a y here and you cross it horizontally and you cross it vertically. And then you go to the right of it. You find az. Okay, az. multiplied by the diagonal component bx minus ax multiplied by b, the two remaining components. So ax b z plus, you delete the crossings, and at first I suggest you do it on paper, the crossings, but try to do it in your mind so you can keep the equation neat and not get confused with all the lines. You make a new parenthesis and you write a z, and then you find a z here, you cross it vertically and horizontally, and then you go to the right of az. In this case it is ax, comes back here, and then you write ax multiplied by the diagonal component, which is by, minus ay cross bx, ay cross bx. And that is the answer. That's how you cross multiply two vectors by each other. The properties of cross product. Now, unfortunately, the cross product is not commutative. The order of multiplication matters. If you want to multiply vector A and vector B together, A cross B, it will not give you the answer as B cross A. In fact, it is called anti-commutative. Which means if you cross A with B, it will give you minus B crossed with A. So if you put A cross B, it will give you minus B cross A in the other direction. So it will be B cross A in the other direction. That's what minus here means. It's direction. It will affect the unit vector at the end. And if you notice up here, if we switch the places between B and B and A, everything here will change. The unit vectors, the components of B will be above and the components of A will be below. That will change the whole answer, but not in magnitude. It will change in direction. It is also not associated. So if we have A cross B cross C, and the parentheses is between B and C, we cannot just take out the parentheses and put them between A and B to make it easier for us. That will give us a wrong answer. But fortunately enough, it is distributed. So if you have A cross B plus C, you can distribute the X inside the parentheses and make things easier for you if that will make things easier for you. Last but not least, the unit vectors. Now, the unit vectors in cross multiplication play a huge role. And if you understood how to multiply unit vectors together, you basically got all of this covered. Now, as we mentioned above, if you have the Cartesian coordinates y, x, and z, and you want to multiply ax and ay together, you will get az or negative az. And now we want to know, is it in the positive direction, in the positive z direction, or is it in the negative z direction? And to know that, we use this thing called the unit cycle. I think that's what is it called? And it is AX, AY, and AZ. And there is an arrow going from X to Y, Y to Z, and Z to X. Keep in mind that there is an order for the coordinates. It is called the X, Y, Z coordinates for a reason. The order is X, then Y, then Z. You can't put XZY or YZX. No, you have to keep it in the same standard, the same order. X, X, Y, and then Z. So X to Y, Y to Z, and Z to X. That's the cycle. And then you look at what you want to multiply. AX cross AY. You look at the cycle. Is the order of multiplication with the arrow, with the flow, or is it against the flow? We look AX cross AZ. It is with the flow of the arrows. Thus, we know that AZ will be positive. Another example, AY cross AZ. We take a look at the cycle. AY, and then it's AZ. Now, we know that the answer will be perpendicular to the both these unit vectors. And what is perpendicular to the Y and Z axis? It is the X axis, but is it in the positive X or is it in the negative X? That's the most important thing, because if you got this wrong, your whole answer is wrong. You take a look at this cycle, and I know it looks weird, but I hope you overlook that. You look AY cross AZ. Is it with the flow? Is it going with the arrows or against it? Well, in this case, it's going with the arrows. We know it's a positive X unit vector. Again, Z and X. What is perpendicular to both Z and X? Well, Y. So we say A, Y. Is it positive or is it negative? Well, I'm going to say positive without explaining why. You should know it by now. Now, AY cross AX. What is a unit vector that is both perpendicular to AX and AY? Well, AZ. But is it positive AZ or is it negative AZ? Well, let's take a look at the cycle. AY, then AX. AY, then AX. It's against the grain. It's against the flow. It's against the arrows. It's at the opposite direction. It's a negative AZ. And then look at this, AZ cross AY. Well, AX is perpendicular to both of them. However, is it a positive X or is it a negative X? AX. We take a look at the cycle. Z then Y. That's against the arrow. So I'm going to put that as negative. AX cross AZ, but it's both perpendicular to Z and X. Oh, it's AY. Is it positive AY or is it negative AY? Well, let's take a look. We have AX, then AZ. Well, that's against the flow, against the grain, against the arrows. Well, it must be negative. Now, I want to have this as a side explanation. What happens when we cross multiply the same unit vector by itself? AX and AX, AY cross AY, AZ cross. If you figure this out, then you understand vector multiplication completely, and that is great. If you haven't, let me explain it to you. It's kind of tricky. Well, AX cross AX, are they perpendicular to one another? The answer is no. They're not perpendicular to one another. Is AY perpendicular to AY? No, it's not. Is AZ perpendicular to AZ? No, it's not. It's parallel. It has no degree angle between them. It's 0. And sine of 0 is, unfortunately, 0, 0, 0. So any unit vector multiplied by itself gives us a 0. Now what about the same vector multiplied by itself? Well, again, A and A are in the same direction. They are parallel. So the answer will be 0. Now, all of what we have talked about concerns two vectors multiplied against one another. Now, what is the case about three vectors multiplied by one another? Well, you can just follow the order of operation, multiply the two together and then the third, and that will give you a fair answer. That will give you the right answer. But what if there is an easier way to multiply three vectors by themselves? The first technique we have, or the first case we have, is called scalar triple product. Now let's talk about the cases that we have. Well, when we multiply two vectors by each other, we have either A dot B or A cross B. We have that sorted out. However, this and this gives us different outputs. This one gives us a scalar output, and this one gives us a vector output. And for us to have three vectors multiplied by each other, we can't have this. If we have vector C multiplied by this, it's a scalar. It's not a vector, so technically it is not three vectors multiplied by each other. It's two vectors multiplied and then a vector with a scalar. So we can't have multiplication that starts with a dot product for it to be three vectors multiplied by one another. However, this case gives us a vector. So if we have a vector that will be multiplied by the output of this, it will be a vector, and thus we will have another vector multiplication. Thus, if we want to have a three vector multiplication, it has to start with the cross product. So the first case is cross product. That's, the first step. Now, we either have another cross product or we have a dot product. And these are the two different scenarios. We have an extra dot product or a cross product after the first cross product. Now, if it was a cross product, the answer will be a vector product, because it's all of these are cross products. And if the final product is a dot product, then the final answer will be dot product. Thus, this is called vector triple product, and this is called scalar triple So, scalar triple product, the first case. It says that the order of multiplication doesn't really matter. By that, I'm sorry, the order of the vector doesn't really matter. If you have A dot B cross C, or B dot C cross A, or C dot A cross B, will give us the same answer. Because at the end, the direction doesn't really matter. It's a dot product. The direction will disappear, and all that matters is magnitudes. So that's a great property to have. But how is there an easier way to do it instead of multiplying twice? Yeah, there's this. And by now, you should know how to solve this. It's not a matrix. This square, I actually don't know what's the name of this. It's just like the one above, just like the vector cross multiplication. You take this out of the parentheses and you cross it vertical and horizontal, and it will give you the answer. However, there is a second way to do it. We will discuss it when the time comes. It's probably in one of the questions in the next video. Now, vector triple product. Well, it says if you have A cross B cross C, there's an actually easier way to do it instead of doing vector multiplication twice. Because vector multiplication is a lot. It takes time and a lot of calculation, and it's easy to miscalculate it. And that easier way is B parentheses A dot C minus C multiplied by A dot B. Now, see this here and this here. This is not vector multiplication. Let me tell you why. A dot C gives you a scalar output. And when a scalar is multiplied by a vector, not vector multiplication, it's just a constant multiplied by a vector. Just do normal multiplication. So we don't have any dot product or cross product in the middle. And that's an easier way to do it, in my opinion. Dot product is very easy. Normal multiplication is very easy. A way to remember this formula is back cap. Back minus cap. The second vector multiplied by the first vector dot the third vector minus the third vector multiplied by the first vector dot the second vector. And a quick note, C multiplied A dot B does not equal A multiplied by C dot B. Don't get confused with this and this. I'm sorry. Between the one above and the one below. They're not the same. There's a cross in between, an additional dot, and like it's different. There's a cross here, there's a dot here, there's a dot here, there's nothing here. In the scale triple product, the order of vectors doesn't matter. However, in vector triple product, the order matters a lot because essentially it's cross product. Components of a vector is the last section in this chapter. Now let's say we have a vector this way and another vector in here. Let's call this vector A and let's call this vector B. And there is an angle between these two vectors. Now, there's an almost an infinite way. There's an infinite ways to describe a vector, but we decided to use the xy plane as a reference to unify. So when you open another book and you see the xy plane, you're going to understand what you're talking about with the reference point 0, 0, 0. But you can describe a vector in terms of another vector. And that is what a component of a vector is all about. You have vector A, and you want to know the component of A in the B direction. You don't want to do it in the X direction or in the Z direction or in the Y direction. You want to know what is the component of A in the B direction. And there's a way for that. It's actually very simple. You say, well, component A in the B direction is equal to vector A dot unit vector A B, and AB equals, and this will give you the B component, the component of A along B. And this is a scalar quantity because of the dot product. But what if you want it in a vector? You don't want it as a magnitude, you want a direction with it. Well, you can. Let's say vector A along B is equal to A dot AB multiplied by A B. Again, just like that, you now have the vector of A along B. This is a vector. You just multiply the unit vector again, and just normal multiplication. And that's how you do it. Let's have a quick recap for everything that we have talked about in this video. Well, vector multiplication. We have two types of vector multiplication. We have the dot product and we have the cross product. The dot product is the product when we multiply the magnitude of A and B and the cosine of the angle between them. And it gives us a scalar output. It's as easy as multiplying the like components. A multiply AX multiplied by BX plus AY BY plus AZ BZ. And when the two vectors are parallel to each other, we get the maximum value, and when they are perpendicular to each other, we get the minimum value. In case of the dot product, it is commutative, it is distributive, and it's easy. The cross product is when you multiply the magnitude of vector A and vector B and the sine of the angle between them, and the result will be perpendicular to both of these vectors. When these two are perpendicular to one another, we get the maximum value, and when they are parallel to one another, we get the minimum value, which is 0. How do we do vector multiplication? We open a parenthesis and rewrite the first value on top, which is the x unit vector. We cross it vertically and horizontally, and we look what's right to it. We find AY on the top. It is AY. We multiply it with what's diagonal, and is BZ. minus the remaining two, AZ and BY. And we do the same for AY and AZ. Cross product property. It is not commutative, it's anti-commutative, meaning that the order of multiplication matters in vector multiplication. A cross B does not equal B cross A. In fact, A cross B equals negative B cross A, because direction here matters. It is not associative. In other words, we can just take out the parentheses and put it whatever we want to make it easy for us, which is very unfortunate. But it is distributive. If we have A cross two vectors added to each other, we can distribute the cross product in the addition. And unit vectors, if we want to cross multiply any two unit vectors, the answer will be perpendicular to these two unit vectors. And how do we know if it's in the positive or in the negative direction? Depends on the cycle. If it's against the cycle, then it is negative. But if it's with the cycle, with the flow, it is positive direction. And any unit vector multiplied by itself will give us 0. And any vector multiplied by itself will give us 0. Triple scalar triple product. If we have two vectors cross multiplied by each other and then a third vector dot product by the answer of these two cross multiplication, we can just have this square that will make things easier for us. Vector triple product. If we have two vectors cross multiplied by each other and we want to cross product the product, there's an easier way, which is back cap. Components of a vector. If you want to find the component of a specific vector along another vector, we can do that by multiplying the vector by the unit vector of the second vector. So we have A, the product unit vector of B, and that will give us the component of A along B. And if you want a vector that is along AB that has the component of A, if we want a vector that is we want to make the components along the vector B a vector, we just multiply it by the unit vector again. I really hope you understood everything in this video, and good luck in your I hope you understand everything in this video, and good luck in your university or in your life.